Welcome to The Explainer. Today we're tackling the ultimate microscopic construction challenge, building incredibly complex organic molecules, like the anti-cancer drug Taxol, literally from scratch. If you've ever wondered how chemists act as molecular architects, linking these tiny, invisible atoms together with pinpoint precision to create life-saving medicines and groundbreaking materials, well, you're absolutely in the right place. Let's get into it.
So how do chemists actually pull this off? Let's dive right into this, because understanding how to connect these atoms is the true key to the whole shebang of organic synthesis. Nature, of course, is fantastic at building elaborate structures, right? But when we want to recreate them in the lab or invent entirely new ones, we have to master the art of forming very specific chemical bonds. And the absolute most fundamental bond in organic chemistry? That's the carbon-carbon bond.
Here's our roadmap for the Explainer today. We're going to start with making carbon-carbon bonds, then move on to generating the carbon nucleophile, kinetic versus thermodynamic control, mastering 3D molecular space, solvents and medium effects, and finally, we'll wrap up with carbon versus oxygen alkylation. All right, Section 1, making carbon-carbon bonds. This is, without a doubt, the ultimate construction challenge.
The whole basis of organic synthesis really comes down to this one crucial point. We've got to carefully fuse a nucleophilic carbon, which is packed with electrons, with an electrophilic carbon, which is electron poor. Fundamentally, we're treating the chemist like a master builder. You can't just toss a bunch of chemicals into a flask, swirl it around, and hope they stick together. You have to perfectly design a scenario where these two specific carbons are basically irresistibly drawn to each other.
To actually make this happen reliably, it's a two-step dance. First up, we use a really strong base to yank a proton off our starting material, and that generates our carbon nucleophile. Then, we react it with our electrophile, which is usually an alkyl halide, via an SN2 displacement. And here's the catch. Our success completely relies on making sure this specific SN2 alkylation is the main event happening in the flask, without any of those messy side reactions getting in the way.
Moving right along to Section 2, generating that carbon nucleophile, which is all about finding exactly the right base.
Okay, before we get completely lost in the chemical alphabet soup, let's define our MVP here, the enolate. When we use our base to pluck a proton from the carbon immediately adjacent to a carbonyl group, that's known as the alpha carbon, we create an anion. Now, what makes this specific anion so special is that it stabilizes its negative charge through resonance. It effectively shifts the bulk of that negative charge right onto the oxygen atom.
Now, if you look at the math behind this, it's pretty wild. To figure out which bases are actually strong enough to completely deprotonate our specific carbon acids, we have to look at their pKa values. The rule of thumb is super simple. You're only going to get a favorable equilibrium if your chosen base has a higher pKa value than the acid you're trying to deprotonate. So take acetone, for example. It has a pK of 20. Meaning you absolutely need a heavy-hitting base like LDA sitting way up there at a pKa of 36 to get the job done right.
This is exactly why we rely so heavily on precision tools like lithium diisopropylamide, or LDA for short. Why is LDA such a rock star in the lab? Well, it's incredibly strong, but its bulky physical shape essentially stops it from acting as a nucleophile and causing all sorts of unwanted side reactions. It gets in, grabs the proton, and gets out. Boom. This is also exactly why we have to use aproduct solvents like THF. We need to make absolutely sure the solvent itself doesn't interfere with our super delicate endulate formation.
Which brings us to Section 3, kinetic versus thermodynamic control. Basically, the regioselectivity battle.
This right here is the molecular architect's rulebook in action. You can actually tweak your lab conditions to totally dictate which enolate regioisomer forms in your flask. Let's say you want the less substituted enolate. You'd use kinetic control. Throw in a strong base like LDA, drop the temperature down to a freezing -78 degrees Celsius, and make that deprotonation rapid and irreversible. On the flip side, if you let the reaction equilibrate at warmer temperatures, thermodynamic control kicks in, and the more stable, more substituted enolate wins out.
I absolutely love this rule from the source material because it's just pure physics. Under kinetic control, grabbing that less hindered proton is simply faster. It's just less crowded. So we essentially win the race before equilibrium even has a chance to set in. We use the massive physical bulk of LDA to our advantage to quickly snatch the easiest proton to reach.
All right, on to Section 4, mastering 3D molecular space. Let's see stereoselectivity in action. Here's the thing, alkylation isn't just a bunch of molecules randomly smashing into each other. There are really strict stereoelectronic requirements at play. The incoming electrophile has to approach at an exactly perpendicular angle to the plane of the enolate. It has to do this to properly interact with the pi electrons. And because of this incredibly specific angle, the 3D geometry of the enolate itself acts like a physical shield. It literally blocks attack from one side and forces the electrophile to the other.
Check out how adding just one simple little methyl group totally changes the 3D geometry of the entire transition state. With a basic cyclohexanon enolate, both faces are pretty much equal, so you end up with a 50-50 mix of products. But the second you add a methyl group at the C3 position, suddenly the lower face is shielded due to a Lillich strain. It physically forces the electrophile to attack from the opposite, unshielded top face. This is literally how chemists dictate the exact 3D architecture of a new drug.
Okay, Section 5, Solvents and Medium Effects. We've got to talk about the working environment.
It is absolutely wild to see the massive explosion in reaction speed when we simply change up our solvent. The rate of alkylation goes from a baseline of 1 in a nonpolar solvent like benzene to 14 in THF, and then a staggering 1,420 times faster when we switch to a polar A-product solvent like DMSO. So, what exactly is going on here?
The secret sauce is all in how the solvent interacts with the molecules. Polar A-product solvents, like DMSO, are just incredible at capturing the positively charged metal cation, whether that's lithium or potassium. But crucially, they leave the negatively charged enolate anion completely bare and unencumbered. Without a bulky solvent cage holding it back, that bare enolate turns into a highly aggressive nucleophile. Conversely, if you try using a protic solvent, like water or alcohol, it hydrogen bonds directly to the enolate, wrapping it up and drastically slowing down your reaction.
Which leads us nicely into Section 6, Carbon versus Oxygen Alkylation, the ambient challenge.
Now remember our main goal here. We want to make carbon-carbon bonds. So we obviously want the reaction to happen at the carbon. To force this, we rely on the hard, soft acid-base principle. On our enolate, the oxygen is small and dense with charge. It's what we call a hard site. The carbon, however, is larger and its charge is more diffuse, making it a soft site. To successfully build our carbon framework, we have to match that soft carbon nucleophile with a soft electrophile. It's like matching puzzle pieces.
When we actually put this into practice, the numbers speak for themselves. If we use an alkyl sulfonate, which features a hard leaving group, it naturally prefers the hard oxygen, and our yield of the carbon alkylated product drops to a pretty measly 11%. But by simply swapping to a soft iodide leaving group on our electrophile, we match soft to soft. This tiny change gives us a massive 71% yield for our desired carbon alkylation, a total game changer. So by mastering these incredibly strong, bulky bases, perfectly tuning our solvents to unmask bare enolates, and playing 3D chess with our molecular space to guide electrophiles, we hold the absolute keys to molecular architecture. This isn't just theory, you guys. This is exactly how chemists assemble the most complex, life-saving compounds in the world today. It really leaves us wondering, with these incredible microscopic tools at our disposal, what impossible molecule will we synthesize tomorrow?